Okay, so let's think about this example in a different way. If I think about this example, really my possible outcomes weren't all of this. That's my possible outcomes for everyone. My possible outcomes for the two young ladies that I was talking about in the beginning, Shanice, I'm going to write it up here, Shanice and Renee, would have been 20 times 19. Let's think about why that is. I have these two young ladies, there's 20 different things that could happen. One person will have the option of 20, the other person will have the option of whatever 19 is left, and that's going to come up with every possible situation that can occur for these two ladies. But the fact is, I want one specific outcome, and that specific outcome is only one way for that to happen, and that's for Shanice to be number one and for Renee to be number two. And so since there's only one way that can happen, I'm going to just put a 1 here. And so you see, I get the same answer we got before, the 1 out of 380, right? Not a big deal. Here's what I do want to talk about, though. I want to talk about how it's related to this permutation thing. The idea of permutations, as we talked about before, we talked about choosing things where order matters. And so it does matter that in this case, that Shanice and Renee get the numbers 1 and 2 respectively. It is not acceptable for them to get 2 and 1, right? That wouldn't be the distinct situation. So order does matter. So the permutation tells me all the ways that I can, with n different choices, that I can choose two or are different things. In our case, 2. So the way I would write in a sense, the sample space that we're dealing with, basically what did we have? 20 times 19. The way that I would write that sample space is really to talk about the sample space being 20 things, choosing where order matters, 2 at a time. All right. And so we might say 20 choose 2, the permutation of 20 choose 2. Okay. And so that would be given by this formula. This value here is given by this formula. You take n factorial, 20 factorial, and you divide it by n minus r factorial. Well, if n is 20 in our made up situation, minus, or in the situation that we just had, minus r, which is 2, would be dividing it by 18 factorial. So to figure out what belongs in the denominator, we would take 20 factorial divided by 18 factorial, something that we did over here, right? 20 factorial and 18 factorial were there. And then what we would do is cancel out the overlap, right? So the overlap would be 18 factorial in the numerator and denominator, like 18 times 16 times 17, blah, 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 blah. 18, same thing here. And then what we end up with is what we just saw, 20 times 19. So in a way, permutations is what gave us the sample space for our situation, and still there was only one desired outcome, so we got that answer in that way. So remember, the permutation just kind of tells me, it gives me a way to count up the number of different possibilities for a certain situation, and you can see this example is down here. Let's go ahead and do another example. All right, so we have example 2. A class is divided into teams, each made up of 15 students. Each team is directed to select team members to be officers. If Sam, Valencia, and Deshane are on a team and the positions are decided at random, what is the probability that they are selected as president, vice president, and secretary, respectively? So as usual, we need to consider the desired outcome over the possible outcome. And really, we only have one desired outcome. That is for this group of people, Sam, Valencia, and Deshane, to be president, vice president, and secretary, respectively. So that indicates that we want it in exactly the same order. That's the one thing that could happen. And there is one way that those 3 people can have that situation, and that's for it to be that way. And again, I'm just considering these 3 people at the time. Now the denominator, all the possible outcomes, will be the ways that you can choose out of 15 people, right? The way you can choose where order matters, 3 different scenarios, right? So or like three different people. So this would be all of our possible outcomes. And so do you remember how to calculate it? We had it up here. We were going to take the n factorial, so factorial, 15 factorial divided by n minus r factorial, or 15 minus 3. And so it comes out to be 15 factorial over 15 minus 3 factorial, which ends up giving me 15 factorial over 15 minus 3 is going to be 12 factorial. And so ultimately we end up with 15 times 14 times 13, which kind of speaks to a logic that we could have, right? If you're picking three things out of 15, the first thing has a possibility of 15 different choices. The second thing now reduces and only has 14 different choices, and the third thing will have 13 different choices. So that kind of makes a certain logical sense to me as well. All right, so this would be our answer. I'm going to erase this work because it's looking a little messy. This would be our answer. And so when we calculate that, we get 2,730. 1 out of 2,730 would be our probability. The next concept we're going to talk about is the idea of the number of permutations you could have in a situation where you've got like repeated values. So for instance, let's say I had the Scrabble tiles T, O, and O. Obviously I can spell the word two, but how many different organizations or ways that I organize these tiles? And so just because they're three different tiles, we would think, well, 3 times 2 times 1, or of course that's 3 factorial, there should be 6 different ways. And so let's make this a little bit more clear. I'm going to change the color of one of the O's to blue so that we can see what exactly is happening. So, all right, so there's 6 different things that's happening here. So one, it would be to have the red T and the red O and the blue O in that order, and I've rewritten it this way, but then we could switch those O's around, and then we could reorganize it in this way where it's OTO, and of course we've got 2 distinguished ways of doing that, and then OOT and then OOT. However, so this does give me 6 different possibilities. However, these possibilities aren't distinct, because if we had identical values, or if we were playing Scrabble, or if we were doing something where these O's were identical, everything was in the same color, then I would be kind of repeating some certain things, right? In fact, I would be repeating, this would be a repeat, this would be a repeat, and this would be a repeat, or an indistinguishable different outcome. So the way you will figure out the permutation of such a situation where you have things that repeat is that you would take the number of things, which is 3 factorial, or you take it and you find 3 factorial, but then you would divide it by all the repeating things. I've got an O that repeats, and so how many of those do I have? I've got 2. So you would do 2 factorial. So then 3 factorial divided by 2 factorial is 3. And so you see that we get 3 distinct possibilities. That was a little cumbersome. Here's how you see it in generic terms. Let me make this a little bit smaller for us. Here's how you see it in generic terms. The number of distinguishable permutations of n objects in which an object is repeated r sub 1 times, an object is repeated r sub 1 times, another is repeated r sub 2 times, and so on. You would write it like this. You would take n factorial, and then you would take the factorial of the number of times each of the things are repeated. So notice it's because I have 2 zeros here, 2 O's, it's repeated twice, that I use 2 factorial. So that's what our situation is. Let's use it in this next problem. Ooh, look. On a game show, you are given the following letters and asked to unscramble them to name a U.S. river. If you selected a permutation of these letters at random, what is the possibility that they would spell the word Mississippi correctly? So the first thing we should do is establish our sample size, right? So there's one way to spell Mississippi. Okay. But we need to think about what our sample size is. What are we thinking about? How many different distinct ways can we organize this? And so we know that we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 factorial, different ways of organizing all of these letters rather. And then we know that there are some repeats. And so we need to divide out the number of times that the repeats repeat. So I have how many I's? I've got 1, 2, 3, 4 I's. So I'm going to divide out by 4 factorial because there's 4 different ways to organize these 4 I's such that we get a repetition of 4 factorial or 24 different things that are actually the same. I hope that made sense. It makes sense in my head. Same thing with these S's. There's 4 of them. So I've got to divide out by another 4 factorial to show the repetition of those S's. M doesn't repeat, but P does. 2 factorial. So let's write it like that. So what I see here is that I don't have 11 factorial distinct possibilities. I have 11 factorial divided by 4 factorial divided by another 4 factorial and divided by 2 factorial for the number of times each of these things repeats. Using a calculator, I get that 11 factorial is really 39,916,800, and 4 factorial times 4 factorial times 2 factorial is 1152. When I divide those, remember what I'm getting here. I'm getting the true distinct sample set that I'm working through in order to get 1 Mississippi. So when I divide those two, I end up with 34,650 different unique representations of these letters. And I've taken out the copies. And so my denominator should be 34,650. So 1 out of 34,650 different trials at looking at organizing these letters will give me the word Mississippi. So far, the types of organization that we've been talking about has been linear, where there's been like a first, second, third, fourth, and fifth place. So each of these refers to a distinct organization of, let's say, in this case, spices. But sometimes we can consider the idea of a circular permutation. So if it's circular, in a sense, what matters is the arrangement of the objects in respect to one another, not so much their location. Because if you think about a circular arrangement, circles turn, circles can spin. So in this case, we see thyme, curry, salt, pepper, and ginger. And again, in this case, though it looks distinct, it's the same: thyme, curry, salt, pepper, and ginger. So when we think about circular permutations, if I have in a sense n number of objects arranged in a circle with no fixed reference point, meaning there's, the circle turns in a sense, then what I will do is I will say that the variety or the various number of ways that we can actually organize those would be n factorial divided by n, or n minus 1 factorial. Okay, so that's what we have, and you can kind of test it out and play with the idea. It really does make perfect sense. Let's look at this example for the probability and circular permutation. Find the indicated probability, explain your reasoning. In part A, if 6 charms on a bracelet are shown and arranged at random, what is the probability that the arrangement shown here is produced? Well, you see what we've got. We've got 6 different objects arranged in a circle. So what really matters is how they orient with one another. Our rule tells us that it's n factorial divided by n, which gives us n minus 1 factorial. And so in this case, it would be 6 minus 1 factorial, or 5 factorial. So there are 120 different arrangements that we could have with that charm bracelet. Excuse me. You are seated at a party of 4 at a round table. One of the chairs around the table is next to a window. If the diners are seated at random, what is the probability that the person paying the bill is seated next to the window? So this isn't exactly a circular permutation, even though we're talking about a round table. Technically, this is pretty linear, and it kind of basically works out to 1 out of 4. The reason why is because if you're randomly generating seats and people can randomly sit down and one seat is by the window, it's 1 out of 4 chance that that person paying the bill is there. Another way of looking at it, if you consider all the possibilities, is that there are 4 factorial different ways to organize these people at the table. There's one thing that I want the person paying the bill to be at that window. There are 3 factorial ways of placing the other people, which leaves 1 out of 4.